Today we're going to talk about the Hausdorff measure and the Hausdorff dimension. So this is, you might have heard of fractals, so this is of interest for that area. And yeah, so let's see what it is. So Okay, so let's take a positive real number and a non-negative real number, and let's take a subset of Rn. And now we want to define the Hausdorff measure. So this is not yet the Hausdorff measure, but it will be used to define it. And afterwards we'll define the Hausdorff dimension by using the Hausdorff measure. So we take the diameter of some sets ui. Probably you already have an intuition about that, but I'll tell you what it is exactly later. And we want, I forgot a sum. So here we have a sum of some countable set of ui's, and we want that this union of the ui's is a what's going on? So here we want that this is a delta cover of f. So now we have two questions. So what is a delta cover and what's the diameter? So let me first tell you what a delta cover is, because the diameter will also occur. Then I'll tell you what the diameter is. So this just means that the diameter of all sets is, not less than infinity, less than delta for all positive integers, and that it covers f. So we want f to be a subset of this union. Okay, so that's it. Delta cover and the diameter, that's quite intuitive. So we take just the supremum over all elements in our set. And then we look at the norm of the difference, and in our case we will be interested in the 2 norm. So that's the diameter, and so let's look at the definition again. So we take these diameters to the s, and we look at all delta covers, and then we take the infimum. Okay, so that's quite straightforward. Well, the definition isn't that obvious, but it's straightforward what the terms in the definition are. Okay, now we want to define the measure. So the thing we have to note is that if we let delta go to 0, this thing can just increase. Or it can decrease, because all the covers for smaller delta are also covers for larger delta. So this is non-decreasing, and so we can look if we go to 0. So we can take the limit, and we note that this limit exists. And now this is the Hausdorff measure. And of course one would have to prove that this actually defines a measure. So that's not clear from the definition yet, but we won't do this here. But now we look at some properties of the Hausdorff measure. So let's look at this S now, because this will be interesting for our Hausdorff dimension. So we have, let's look at the things that occur in this definition. So we have the sum over the diameters. And now let's look what happens if we let if we make S a little bit bigger by some epsilon greater than 0. And then, well, we know that the UIs are delta covers, so we know that this is at most this thing here. And now let's look at the definition. So we have this limit for delta going to 0. So if we have that this measure is finite, we get that there is some cover for which the sum is finite. And now if the sum is finite, then this thing here converges to 0 for delta going to 0. So this means actually that the Hausdorff measure with parameter s plus epsilon is 0. So let's look at this graphically. So here we have graph. So well, I guess you can get what it should look like. So here we have the parameter s. Here we have the Hausdorff measure. Here we have infinity. And here we have 0. And then we have a point which might lie on this line or here. Or, well, it might also go to infinity here, but there exists something which can be infinity where we have a jump. So we have a jump from infinity, then there might be some intermediate point, or it might jump straight to 0, and then afterwards it's 0. So there's at most one point for which it's the Hausdorff measure of f is not 0 and not infinity. There might be also no such point, so it can be okay. So let me first define now the dimension with that knowledge, and then let me tell you a little bit more. So we define the Hausdorff dimension of the set f to be the infimum of all non-negative numbers, such that the Hausdorff measure is 0. So that we go along this thing here, then we look at the infimum where it's 0, or we can also define it as a supremum. And well, that's obviously the other way, so we go, maybe let me take colors, so we go here, and then of course that's where it's infinity. And well, one has to be a little bit careful if the dimension is 0. This here might be the empty set, so well, one would have to be a little bit careful, but in general these two things are the same. And as I already mentioned before, so for s equal to the Hausdorff dimension, we can have that the Hausdorff measure is in this set. So it can be 0, it can be some non-zero finite thing, or it can also be infinite. So all these things can happen, and well, one has to find out what happens at the point of the dimension. Okay, so these are some first properties and definitions, and now let's look at a simple case. So let's state a lemma. So let's look at the Cantor set. If you don't know what the Cantor set is, I recommend you to look it up. You can also look at Cantor function, which is also quite interesting. Well, I can also give you a short sketch. So let's take the unit interval, and then we take out the middle third. So then we have these two intervals left, and we take out the middle third in these two, and we do this again and again. So now we have this left, and this left, and this, and in all the left the intervals we still have, we take out the middle thirds. And yeah, we do that. Then we take the limit for n go into infinity. So we have these sets, and then we get a Cantor set. And the lemma is that the Hausdorff dimension is the logarithm of 2 divided by the log of 3. Okay, so I won't prove it here, maybe I'll prove it in another video, but let me show you the idea. So let's say S is equal to the Hausdorff dimension. And now we make a rather strong assumption. One would have to justify that. So this is, we assume that the Hausdorff measure at S equal to that dimension, that it's here not infinite and also not 0. So that's our assumption. And now we go on. So what is the Hausdorff measure? And now we use a scaling property. You can try to prove this on your own, but let me also motivate it later a little bit. So at first, so let's see, what do I say here? So here I say we have the Cantor set, and then instead of looking at the Cantor set, we look at the union of this so we can split the Cantor set in two sets. And basically these two sets are again the Cantor set, just scaled by a factor of 1/3. And so the 2 comes from these two sets, and as it's scaled by 1/3, we get with the scaling property 1/3 to the s, and then the Hausdorff measure again. And so to motivate, one can calculate this scaling property directly from the definition here of the Hausdorff measure. But let me motivate it a little bit more. So if also for, let's think of just some some normal volume you would think of. So, for instance, think of the volume of a rectangle in two-dimensional space. And then if you scale this volume, then you get, let's say, f is this rectangle, and then we get the volume of lambda f is lambda squared volume of f. So that's a normal scaling property, and this Hausdorff measure also satisfies such a scaling property, and in more generality, and also up to some constants. Actually, the Hausdorff dimension for for positive integer values is the Lebesgue measure. So at least for if you know that, then you know that how it's for positive integer values, and you can easily calculate it from the definition here that it holds in more generality. Okay, so that's how we come to this equation. And well, now here comes our big assumption, because this enables us to divide by hf of c, so we get that 1 is equal to 2 times 1/3 to the s. We take logarithms, so we get log 2 plus s, or let's make it immediately to a minus s, log 3, and that gives us this dimension here. Okay, so that's the Hausdorff dimension of the Cantor set. Well, if you want to know an example where this reasoning fails, so I told you this idea and said, well, if we have that, we can do this. Where it obviously fails is if we have, let's look at, so where we can't do this is if we would look, instead of at the Cantor set, we would insert here, again, let's say, the left part of the Cantor set in the middle. Then this, if we would apply this reasoning again, then we would get that, well, no, that's actually wrong, because these sets are not exactly self-similar. Again, let me think. No, I think what I said is wrong. So yeah, probably you would have to think a little bit more. And I also have an example where this fails. Okay, but anyway, so that's more or less what I wanted to say in this video. So one more remark. So interesting maps for Hausdorff dimension are Lipschitz maps, or in more generality Hölder continuous maps. And probably in the next video I'll tell you a little bit about Lipschitz maps and about so that polynomials preserve the Hausdorff dimension on the real line. Well, I don't take this statement about polynomials for granted. I'll check it again, and I hope that my proof is correct. But I'm not sure yet. I also haven't checked the literature yet, so take this with a grain of salt, but I'll check it again, and if it's correct, I'll show you next time. And yeah, this will be important for the dimension. And yeah, that's it for this video. Also, you can try to look at some other sets and try to calculate Hausdorff dimension for these sets. And there are some examples you can find on the internet. And yeah, that's it for today. I hope you had fun, and maybe see you next time. Bye.